All right, as promised, we're going to build a computational model of the falling sphere with a simple Euler method. And I'm going to do this in Matlab. Um, Once you see this implemented in a particular language, then it's pretty easy to follow along other languages. We're going to use the basic components of a computer language, and the difference between Matlab and some others is just syntax for the most part. So I'm going to use Matlab just because it's available. Keep in mind, as I put in the syllabus, you don't have to use Matlab in this course for carrying out the computational projects. If you want to use Python or C or whatever, that's fine. But I'm going to take you through this in Matlab. And again, seeing this in a specific language will make it clear how to go about it in any language, because the components are more or less the same, right? So now what you're looking at here, what will look a little bit different for different what we'll call computational platforms or computing environments, is the starting point. So this is the Matlab command window, all right? And this is what you'd see if you fire up Matlab on either one of the computers in the computer lab, or if you have a personal edition. I'm assuming also that you've gone through a sufficient amount of tutorial material to get you into Matlab and get started, or that you have some level of, I don't know if I call expertise, but experience with Matlab to follow along, although I'm going to explain every step, and I think you'll be able to understand what's going on. But it's really important that you have go through some of those tutorials and some of the things I've posted, or have found some tutorial materials online to get you up to speed with Matlab, at least to a basic level, right? So let me just point out a couple things about this computing environment here. There's this thing called the command window. You can see the blinking cursor here. This is sort of the central location where Matlab does its thing. The command window is where you, as it's called, you type in commands. The way Matlab works is it's called an interpreter, and it's just waiting for you to put a command in. And once you put a command in, it'll do what you've told it to do, right? So that's this command window. I don't want to so much emphasize the use of the command window in these things here. Again, hopefully you've gone through and are up to speed on some basic Matlab stuff. So I'm going to kind of go quickly through this. This workspace window over here is where a list of all the variables that we're going to be using in the program will appear once we run it. This is particularly useful for if you want certain values you want to get out, you can look at them here. But also this is very useful for debugging if you make a mistake. Right? Over here is it's called, it says name here, but this area over here where my little arrow is wiggling around, this is very much like a Windows Explorer. It's kind of a file management system, right? So again, I'm assuming you've played with this, and so I don't really have to describe too much of what's happening. I have a working folder up here. You can see the path in here. This is on my C drive, and you can see where I'm working. I've created just an empty folder, and that's where everything that I'm going to create right here is going to go into. All right. All right, so the first step, we're going to create a program, a Matlab program. The specific word for a Matlab program is called a script. We're going to actually create a .m file. That's the suffix for Matlab scripts. The reason it's called a script, I'm not entirely sure why, but I think it has to do with that this is an interpreter and it's looking for a script. I guess that's why they call it a script. Right? So we're going to use the word, at least in the context of Matlab, we're going to use the word script, and we're going to use the word program interchangeably. All right. So I'm going to create a program called, we'll call it Falling Sphere. All right. Why not keep it simple? Right. So there's a couple ways to create a new script. You could do it up here on these icons up here. You could click new script, and that would do it. Or you could do this, edit, I'm going to call it falling. I'm going to use underscore sphere. The scripts have to have a single name. So if you want two words, you could run them together, or sometimes it's nice to separate them with this underscore here. All right. And so if I hit enter, there we go. I don't know why we're so slow. I get this dialog box that pops up, and it says, you can see here, it's wanting to put it in my path that I have specified. It says file, blah, 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 falling sphere.m. It automatically knows I'm wanting to create a .m file. It says it does not exist. You want to create it, and I'll say yes. All right. And it will automatically create it for me. I don't know why we're so slow. All right. And you can see what's happened. Let me move this over. This is the script file, by the way. This is a window that pops up in MATLAB called the an editor window. All right. All this is really just a text editor that is attached to the MATLAB command, or the MATLAB interpreter. So if I put text in here, then I say run, it will do what I tell it to do. But it will only do all the commands I type in the script. It will only do it if I indeed tell it to run. It won't do them one at a time like it would in the command window. You'll notice over here in this file management system, it did indeed create a file called fallingsphere.m, and it put it in my current folder, which I have specified. Right? So let's go over here now to this editor. Right? And I'll just maximize this window. So here's the editor now. And here's where we're going to start building our falling sphere model. So I'm going to type in commands, and I'll talk you through it as I type them in. At any point, the nice thing about this video, of course, I'm not there with you personally, which means we could interact. But nice thing about the video, you can stop it, and if you have to, go look up something in the MATLAB documentation or type it into Google. All right. So the place I like to start with any MATLAB script, I like to do two things. All right, CLEAR, clear. All right, and I like to use the CLC command. All right, this is just a good starting point. What clear does, it clears out all the variables that have already been defined for the interpreter. So in other words, if you've already built a script and you run the script, and then you start maybe working on a new script and you run it, there may be variables that the interpreter thinks you have defined from the old program, and it might actually try to use them for the new program. So this is just a good programming procedure to clear everything out so that there's no crosstalk from previous programs, right? That's what clear does. It just clears out all the memory locations and clears out all the variables, right? CLC means command line clear, or clear command line, or something like that. And what that does is if you have any output, what I've done is gone back to the command window here. That CLC clears the command window. Let me just demonstrate what it does here, right here. So if I type CLC, it just goes up to a starting point in the command window, and it gets rid of everything that was already typed in there. Right? It's just makes it clean. It makes it easy to debug if we ever need to. All right. So those really aren't going to do much for us. Oops. Let's go back to the script file, the editor file here. It's clear and CLC aren't going to do much for us. They're really irrelevant to the program we're writing, but it just sets up the interpreter to do what we want it to do in our falling sphere program. Right. So now the first thing I'm going to do is type in the variables or the parameters that we're going to use. Parameters, variables, I'm going to use these terms interchangeably. We need to set the values of some things that we're going to use. All right. So, and I'm going to do something here. The percent sign, I just did an uppercase 5, that gets that percent. Whenever you do this, is called a comment. I'm going to put define parameters. All right, whenever there's a percent sign, you can see in MATLAB, the MATLAB editor, it turned the letters green here. That means it's going to ignore, the interpreter always ignores everything behind the percent sign. Right? So that's called a comment. And I just did that to make it clear what's coming next in the program, right? So we're going to define parameters. Now, what parameters do we need? Let's go back to the equation we came up with when we applied Newton's second law to the falling sphere. Right? You should recognize this. This is the acceleration after we did a little bit of algebra solving for A, after we set the net force equal to F equals ma. So I'm looking at this top equation here. And by parameters, I mean the numbers or the values we need to use in our model that we're building. You can see there's 1, 2, 3, 4, 5 altogether. The acceleration due to gravity, our good old friend g. We need a drag coefficient, density of air, an area, as well as a mass. Right, now we'll need a couple more things that we'll have to specify, but these are the physical parameters. These are the physical parameters associated with our model. Right? So let's put those in first. Let's go here. Oops, I went to the command window. Let's go here. All right, and let's define these. So remember, we needed first of all a mass. All right, now let's pretend that we're going to make this interesting. I mean, we just don't want to drop a sphere. That'd be kind of boring from some little building, right? Let's drop it from the Sears Tower. Now that'd be exciting. You probably know that I think they changed the name to Willis Tower. It'll always be the Sears Tower to me. That's that big building. Used to be the tallest building in the world. That would be really cool if we could drop a basketball, for instance, from the Sears Tower. Wouldn't that be a cool experiment to do? The answer is yes. Right, but we need, if we're going to drop a basketball, we need to use the mass of a basketball. Now we could either look this up, or I think I somehow know this. But keep in mind we're going to use MKS units too, by the way. Right. So I think the mass of a typical basketball is something like 0.625 kilograms, and so I let m equal 0.625, m for mass. By the way, when you build these programs, you may as well use variables that make sense. So m for mass, it would be silly if I used x for mass. That would be very confusing if somebody were looking at this. Now, if I were going to do this very strictly and document my program for others to look at or for notes to myself in the future, I might actually put a bunch of comments in here. So for instance, see, I put another percent sign here. Mass of basketball in kilograms. In other words, I put a comment. Remember that the interpreter will ignore everything after the percent sign. So this is the mass of a basketball in kilograms. Right? And there's that note, so it's obvious what m is. M for mass, but then I also have this other comment here. And it's absolutely clear what that is. Now, I'm not going to do this in detail for everything we do in this program, although just to save so the video doesn't become that excruciatingly long. But I would urge you to do this yourself as you build your programs. All right? So I just wanted to demonstrate that for one of these things. One other thing to point out here, notice the little semicolon. See that right there? The semicolon I put after the number? If you don't include a semicolon there, the interpreter will spit that number out at you. In other words, it'll print the number right back here on the command window once you run your program. If you don't want it to print out everything, just terminate what you don't want printed out with a semicolon. Now that, again, can be useful if you want to know a value for whatever reason, or if you want to debug something. You got a program that's not spitting something out that makes sense, you might want to debug it, and that becomes useful to take the semicolons out. Right, so just keep that in mind. Semicolons suppress the output. All right, what else do we need? We need a row. Let's just call it row. All right, RHO. That's in our equation back here. Let's look at it again. This is this density of air, lowercase Greek rho. Right, that's the density of air. Since we're going to drop the ball close to the surface of the Earth, I mean, the Sears Tower, I believe the observation deck is at something like 440 meters relative to the pavement. If that means we're not really that far from the surface of the Earth. I mean, yeah, it's a tall building, but on the grand scale, it's essentially close to the surface of the Earth. So we're going to use a density of air which is comparable to the density at sea level. Right? And let's go back to our Matlab script here. And rho will equal, and I just happen to know this also, 1.29 kilograms per cubic meter. All right, density of air. Okay. And MKS units is kilograms per meter cubed. Right? So again, I'm not going to do a comment for all the parameters. I'm just doing that for a couple to urge you to get in the habit of doing it. All right, what else do we need? Right, well, another thing we need is our good old friend G, acceleration due to gravity. G for gravity, you may remember this close to the surface of the Earth is 9.81 meters per second squared. Again, notice I'm using a semicolon to terminate everything. All right, and if you look over, let's look at that equation one more time. G, D rho A, we need a D. Now, you may remember I said we're going to pretend that D is constant to start with. And when you get to your first project, you're going to realize, or I'm going to have you investigate what happens when D is not constant. So we need a D, but we also need an A yet. Right? So I need a drag coefficient D, and I need this frontal area, or this cross-sectional area A. So go back to the script. All right. Let's put D in. Remember I said we're going to use D for drag coefficient as 0.5. That's a pretty good number for a smooth sphere, but you'll see soon enough how that deviates from 0.5. So this is actually a very simplistic model that we're building by assuming that D is constant. For now, it's all right. What else do we need? We need air. So we need the area of a basketball that presents the area that, in not just the volume, of course there's the volume of the ball, but we need the area that's presented in the direction in which it's moving. So if you saw a basketball thrown at you, or a baseball, or some sphere thrown at you, you would see a circular area. Right? And that's really what this A is. Right? So I would suggest, though, instead of calculating the A directly, why don't we input the radius? Right? In other words, I'm going to define R. And let's look this up. Offhand, I'm not entirely sure. I'm going to type into Google radius of basketball. Okay, and let's see what comes up. All right, so here we are. Men's ball and a women's ball. Let's use a men's ball. Not that I have anything against women, but this is just the first number that pops out. The men's ball is about, now this is in diameter, notice this, and we want NKS units, so 24 centimeters. Let's round it to 24 centimeters. In meters, that would be 0.24, but that's the diameter. We need the radius. I'll show you why we need the radius. So let's go back to here, and we'll let the radius be 0.12. That's half the diameter. Okay, and we'll just make a comment here. Radius of basketball in meters, all right? Now, the reason I used radius, because that was easy to look up. Let's say we wanted, after we run this program, we wanted to change our sphere that we're dropping to a baseball. All we would have to look up is the mass of a baseball and substitute that number in. And all you have to do then is look up the radius of a baseball rather than the cross-sectional area, because we can calculate this, right? A equals pi r squared, right? That's the area presented. That's the area of a circle of radius r. And I'm just going to put this number in for pi. 31415.9. We have 5 digits is fine for pi. Star r raised, upward pointing arrow, to the 2 powers. See that? Right, so that way, if I look up the radius of any ball, or if I estimate the radius of a marble, or whatever I want to drop from the Sears Tower, all I have to do is input the radius, and then the area, that cross-sectional area, is automatically calculated for us via 8 pi r squared here. All right, those are all the physical parameters that we need. Now we're going to need 2 more things, right? And I wanted to remind you back here what this little simple Euler method looks like. Do you remember this Euler method in particular? Look where I'm moving my cursor here. Right? Look what we're going to need. We're going to need a couple things actually. We're going to be predicting for every successive time step what the velocity is at the previous time plus delta t. That means we're going to have to get this iterative process started. So we need to know the initial velocity, and if we do it for position 2, we need to know the initial position, but we also need a value of delta t. Now, remember, the only criterion we have for this equation, this approximation, remember it's a wiggly equal sign, the only criterion is that delta t has to be pretty small. Right? Now, we don't know what delta small means yet, and we're going to have to, once we've built our model, we're going to have to investigate this a little bit. Right? But let's go back here and we'll put those things in. We need an initial velocity. All right, and so I'm going to call it V underscore. I like to use underscore to imply a subscript. So that's like V subscript 0. See that? That's initial velocity. But let's just drop our ball from the Sears Tower. Right, let's not throw it. Let's say we're standing, I don't know if I'd want to be standing outside, but standing outside on the observation deck, at least a distance equivalent to the observation deck at the Sears Tower. And I'm just going to hold my ball and then I'm going to drop it. So that means the initial velocity is 0. Don't forget to terminate. And furthermore, let's call the initial position. Remember when we defined our acceleration for the falling sphere, we called the down direction positive? Let's call the initial position also 0. That means the level of the observation deck is 0. Since the down direction is positive, the pavement will be located at about 440 meters. Positive 440 meters. All right? So just keep that in mind. We're defining the initial velocity and the initial position both as 0. We're dropping the ball and we're starting at point 0, and position will increase as it goes down, as the ball falls. We also need that delta t, right? So instead of getting a capital delta, I'll just use little dt. Right, now remember, this has to be small. Now I don't know what small means. That's a relative thing. We're going to have to investigate this actually, and I'll demonstrate how we do that. But for now, I'm just going to dial in a value of 0.1. Right, so this is my delta t. This is my time interval. All right, don't be confused by using little dt. This doesn't mean we're implying it's an infinitesimally small time. Right, this is supposed to be capital delta t, but I'm just not going to bother with putting a Greek symbol in. Right. All right, so that's delta t in seconds. Right? Now, there's one more thing we've got to do. One more parameter we got to define. We got to tell the computer how many times we're going to calculate this. In other words, how many iterations are we going to over and over again approximate the value of the velocity and the position using our acceleration that we got from Newton's second law. We got to tell it how many times to do this over and over again. So I'm going to use little n. Right? Just little n, and I'm going to make this, I don't know, just to start out, we'll do it 1,000 times. Right, and I'll label this. This is number of iterations, right? Or the number of time steps is what that means. The number of time steps we're going to go through. All right, so far, all I'm doing is defining parameters. Remember, in a computer language, hopefully you've already gone through the tutorial stuff, in a computer language, the equal sign means assign. So every one of these variables, every one of these parameters has been assigned the value on the right-hand side. In other words, another way to think of it is let n equal is what this means. N is assigned the value of 1,000, or let n equal 1,000. All right? Okay, good. Now I'm going to show you the easiest way to implement the Euler method. The easiest way to do that is by using something called arrays. All right, and so the next major part of the program, I'm going to write another comment, and I'm going to write it like this. I'll write the words, and then I'll explain what this means. All right, we're going to pre-allocate some arrays. This is the absolute easiest way to program something because you're actually using these things called arrays, which is a group of values. It's actually, an array is really a group of memory locations in the random access memory of your computer. And by pre-allocating them, you're defining the positions within the random access memory. All right, so let me show you how to do this pre-allocation step. It's pretty simple. You may have already seen this in the tutorial stuff you've been through, but let me show you how to do this. We're going to actually need to keep track of several things. Ultimately, we want to be able to produce a graph, or the predicted numbers, but a graph is really what we're after. We want to ultimately produce a graph of position versus time as the ball falls down, velocity versus time. We probably even like to look at the acceleration versus time. All right, so I'm going to create a series of memory locations that are associated with each of those physical quantities. So I'll start with time. All right, and here's how you do this pre-allocation thing. There's a command in Matlab called zeros, Z-E-R-O-S, and here's what the syntax looks like. I'm going to do 1 comma n, and then I'm going to terminate it with a semicolon. Now let's look at this, and again, you could You could type in the zeros command into Google, type in zeros MATLAB, it'll tell you all about it. I'll give you a brief description here. If you want to look into more depth, you can. Right? This accomplishes two things. First of all, it says zeros of 1 comma n. The 1 means a one-dimensional array or a vector. All right? And the n here means that there are n. Now, n was already specified as 1,000 up here. Right? This n here means that there are going to be n values associated with this quantity called time. It's called an array. It's a group of values that will be associated with this thing called time. And what the zeros does, it does two things. It pre-allocates, in other words, allocates locations for all 1,000 locations that we want. And really, the way that MATLAB does this, 1 is the row. So this is defining a row vector, or a group of numbers that are all in a row. 1 row, comma, n columns is what that really means. All right? So time now is associated with n values, and all these n values were initialized to 0. That's what the zeros command does. So zeros command does two things again. It allocates a specified number of memory locations, in this case n, and it also sets all of those values equal to 0. Right? Now, you don't necessarily have to set all the time values equal to 0, but it's very useful for pre-allocating and for debugging. Right? Now, we want time. We've got time defined. Now we want position. I'm just going to call it position. Right? We're going to do the same thing, and we're going to make the position, we're going to associate with this name position also a number n of memory locations. And we're also going to set them all initially equal to 0. That's what the zeros command does. We'll do the same with velocity. Once you get used to this, this will make sense, and you'll be able to use this very efficiently. Right? A little funny when you first learn it. Right? Velocity now has been defined as an array, a one-dimensional array or a vector, a row of numbers basically, and each number associated with the n memory locations has been set to 0. Finally, acceleration. And I'm just typing these quantities out. You could use t for time, p for position, v for velocity, a for acceleration. Doesn't matter. As long as you define things and as long as you make a comment somewhere that reminds you what these all stand for. It would probably be not very wise to use a different letter than v for velocity, for instance, or a different word than velocity for velocity. This just makes sense, and it's a good habit to get into. Use descriptive names which tell exactly what the variable you're working with means. All right, so now the pre-allocation is all done. All right. That means the computer knows that with time, position, velocity, and acceleration, with each of those, a number n memory locations should be set aside. All right, now we're almost ready to start building our Euler model of the falling sphere. But one more thing to do, one more preliminary thing, and this is another part of the program. We're going to here specify initial conditions. All right? Now, I'll show you how to do this. Every one of these array values, every one of these memory locations associated with these quantities has a location. The very first location, we're going to let that correspond physically with the 0 time. In other words, time initial will be 0. That's where we usually start things in physics and engineering. But the position, velocity, acceleration at the 0th time will be the initial position, initial velocity, and initial acceleration. And we're going to specify these, but we're going to now use the locations of the arrays to specify this. Right? Now, this will make a lot more sense if you've taken time to go through all of those tutorials. I put tutorials up on the resources, but also you can find all kinds of stuff online. So if you haven't done it yet, it's going to be best if you stop the video and go through and understand a little bit about arrays and how to interact with specific elements within an array and how to index everything. All right? So I'm going to assume that you know how to do this, and what I'm about to do will make sense. Okay? Now in Matlab, we can't use a 0 to specify a memory location. In other words, we have to use an integer value to specify every one of the values associated with the time array, for instance. Right? So the initial time, we want the initial time to be 0. 0 seconds is when we drop our basketball. We're standing at the top of the Sears Tower. At time 0, I release the ball, and it releases from rest. Right? So that means time. Now, I can't call it time of 0. I got to do it like this. All right? Now let's think about what I just did. 1 here is in parentheses. That corresponds to the first memory position associated with time. All right? That's how you index, so that's how you refer to the different locations in this time index. This time array. That's the first memory location. So we may as well make use of that these memory locations are all spread out. They're all defined, well defined as a result of our pre-allocation commands. Right? But we may as well let each successive one correspond to the next time step. Right? So the first memory location corresponds to time 0. Now position, we've already defined y0 up here. So position of 1, which is the initial position, we're going to let equal y underscore 0. Because I've already defined the initial position up here. So now if I just let position of 1, that's the first memory location for position, which corresponds to the first time, which is the initial time, all I have to do is set that equal or assign the value of y0 to position of 1. I can do the same thing with velocity of 1. Equals v underscore 0. Remember, we defined the initial velocity here. I'm dropping the ball, so it's 0. If I wanted to change it, I could. But there was only one place I would need to change it. It would be right here, because I'm setting the velocity of that first memory location equal to v0. I'm assigning it the value of z0. See that? Okay? Next, finally, is acceleration. But now acceleration has a specific equation that we got from Newton's second law. Let's go back and look at it. Remember, a of t is given to us, oops, I think it's in the previous slide, right? Oops, I went too far. Right here. So acceleration, we know the exact expression for it. We're not going to model, we're not going to approximate this. We know the exact acceleration. A at a specific time equals g minus d rho a over 2m times the velocity at that specific time. See that? So that's going to have to be dialed in for the initial acceleration, considering that the acceleration at time 0 equals this stuff, but evaluated at v of 0. All right, well here, let's write it down. You can see it. So I'm looking down here. Oops. Acceleration of 1 equals, now I do what that equation says to do. It's g, let's look back one more time real quick, g minus d rho a times v at that same time step squared divided by the quantity 2 times m. So let's dial that in. G minus d star rho star a, right, times the quantity v at the same time step. What is v at the same time step? That's the velocity here, right? Velocity of 1. That's what I have to put in there. Velocity of 1, and I have to square it, so I'm going to raise it to the 2 power divided by the quantity 2 star m. And I'll put a little semicolon to terminate it. Right, so you can see what I did. D rho a, I did all the denominator, then I divided by quantity 2 times m. All right, so keep in mind the acceleration, the initial acceleration is not 0. we have the exact equation for the acceleration, and we have to evaluate the acceleration at the initial time with the velocity at the initial time. Everyone see that? Hopefully. All right. So those are the initial conditions. Now we're ready to start this iterative process. Now the way you do iterations in a computer language is through what's called a loop. So I'm going to use the Matlab format and syntax for a loop. Take a quick break. Right back.